Introduction: Beyond the Visible Universe. Throughout history, humanity has looked at the night sky and wondered whether what we see is all that exists. For most of our past, the stars were thought to be distant lanterns fixed upon a cosmic dome. But with time, with science, and with imagination, those pinpricks of light revealed themselves to be suns, vast furnaces surrounded by their own worlds. The universe expanded in our minds, and with it, our questions deepened. What if our universe is not alone? What if the stars, galaxies, and cosmic filaments are merely one bubble in a frothing sea of universes? Michio Kaku, theoretical physicist and futurist, has dedicated much of his life to this question. To him, the idea of parallel universes is not science fiction, but a natural consequence of modern physics. Drawing from quantum mechanics, general relativity, and above all, the elegant mathematics of string theory, Kaku has painted a picture of a multiverse far stranger and more beautiful than we ever dared to imagine. In this journey, we will explore his vision, the idea that the laws of physics themselves may be born in higher dimensions, that countless parallel worlds might exist alongside ours, and that through understanding the deepest patterns of reality, we may even approach what Kaku calls the mind of God, the ultimate unity of all laws of nature. This is not just a scientific odyssey. It is also a philosophical voyage, one that challenges our place in the cosmos and our understanding of reality itself. Each chapter will uncover a different facet of Kaku's ideas, leading us deeper into the mystery of the multiverse and the strange beauty of string theory. Chapter 1: The Cosmic Symphony. When Michio Kaku explains string theory, he often uses the metaphor of music. Imagine each fundamental particle not as a tiny billiard ball, nor as a point of energy, but as a vibrating string. These strings are unimaginably small, far tinier than atoms themselves, existing at the Planck scale, where space-time itself becomes grainy. Just as the strings of a violin can vibrate at different frequencies, producing different musical notes, the strings of the universe vibrate in different ways, producing the particles and forces we observe. Electrons, photons, quarks, these are not separate entities, but different expressions of the same fundamental string resonating in the grand cosmic symphony. For Kaku, this vision is more than an elegant theory. It is the closest humanity has come to a theory of everything. Instead of treating gravity, electromagnetism, and the nuclear forces as distinct, string theory proposes that all are manifestations of one deeper principle. The universe, in this sense, is not built from matter alone, but from harmony, from the vibration of strings playing out across the fabric of space-time. But there is a twist. For the mathematics of string theory to work, the universe cannot be limited to the 3 dimensions of space and 1 of time that we experience. Instead, the equations demand extra dimensions, hidden realms beyond our perception. Some versions suggest 10 dimensions, others 11, each folded and curled so tightly that we cannot directly see them. These dimensions, though invisible, shape the string's vibrations and thus determine the very laws of physics in our world. To Kaku, this is where the beauty lies. The constants of nature, the mass of the electron, the strength of gravity, the speed of light, may not be arbitrary accidents, but the results of higher dimensional geometry. In other words, our reality could be the product of invisible shapes curled up in dimensions smaller than atoms. And here arises the doorway to the multiverse. If there are many ways to fold and curl these extra dimensions, then there could be countless possible universes, each with its own set of laws. Our cosmos, with its galaxies, stars, and life, is just one melody in a vast cosmic orchestra. Michio Kaku often reflects on this idea with a sense of wonder. He recalls how Einstein once spoke of wanting to know the mind of God, not in a religious sense, but as a metaphor for the deepest order of the universe. For Kaku, string theory and the multiverse may be humanity's best attempt yet to touch that mind, to glimpse the architecture of reality itself. And so the cosmic symphony plays on. Every star, every atom, every thought in our minds is a note in this music. And somewhere, beyond the veil of the visible universe, other melodies may be playing, parallel worlds born from the same fundamental strings, resonating in dimensions beyond our sight. Chapter 2. The Cosmic Symphony. Strings as the fundamental notes of reality. In the great tapestry of modern physics, few metaphors are as captivating as the one Michio Kaku so often invokes: the universe as a grand symphony, where the very fabric of reality is composed of vibrating strings. To understand why this imagery resonates so deeply, one must travel back to the early dreams of unification, the idea that the laws of nature, so varied in their expression, might all arise from a single principle, a single framework that underlies existence. String theory was born from this dream. At its core, it proposes something profoundly radical: that the building blocks of the universe are not point-like particles, as traditionally imagined, but minuscule, one-dimensional strings of energy. These strings vibrate at different frequencies, much like the strings of a violin or a harp. And just as the same instrument can produce many different notes, the universe can generate the multitude of particles and forces we observe simply by changing the mode of vibration. In Michio Kaku's poetic framing, this means that electrons, quarks, photons, and even the force of gravity are not fundamentally different entities, but rather the notes of this cosmic symphony. Each particle is a vibration pattern, and the laws of physics are the harmonies that emerge from their interplay. Instead of chaos, there is music. Instead of randomness, there is order written into the geometry of higher dimensions. Yet this vision is not without challenges. One of the most striking aspects of string theory is that it requires the existence of extra dimensions, hidden realms beyond the familiar three dimensions of space and one of time. According to the theory, the strings need additional dimensions in which to vibrate in order to produce the full spectrum of particles and forces. These dimensions are thought to be tightly curled up, compactified in ways so small that they escape our perception, hidden within the quantum structure of space itself. Kaku often compares these hidden dimensions to the unseen layers of a cosmic onion. We live on the outer skin, perceiving only what our senses allow, while beneath the surface lies a far richer architecture of reality. These extra dimensions, though invisible, may hold the key to unlocking mysteries such as gravity's weakness compared to other forces, or the possibility of entire universes coexisting alongside our own. One of the most elegant implications of this theory is its treatment of gravity. For centuries, gravity has resisted unification with the other fundamental forces of nature, electromagnetism and the strong and weak nuclear forces. But in the framework of string theory, gravity emerges naturally. It is not an outlier, but an integral part of the cosmic symphony, a note played on the same instrument as all the others. This insight suggests that string theory could, at last, fulfill the ancient quest for a theory of everything. Kaku often explains that the mathematics of string theory is daunting, like deciphering a new musical score written in alien notation. But when physicists listen carefully, the equations whisper of beauty, symmetry, unity, and infinite possibilities. The theory hints at a multiverse, a vast ensemble of universes, each with its own version of the symphony, each a different song in the great orchestra of existence. Critics, of course, point to the lack of experimental evidence. The strings are thought to be on scales so small, billions of times smaller than an atomic nucleus, that no experiment currently available can detect them directly. To many skeptics, this makes string theory an elegant but unverifiable hypothesis. But Kaku argues that this is precisely how scientific revolutions begin, with ideas that stretch beyond current technology, waiting for the tools of tomorrow to reveal their truth. Beyond the technical debates, what makes Kaku's vision so compelling is his ability to convey a sense of wonder. For him, string theory is not only about equations on a chalkboard, but about humanity's place in the cosmos. If the universe is a symphony, then perhaps consciousness itself is part of the music, our minds emerging as the universe listens to its own song. To ask, what is reality, is to ask, what is the melody of existence? The cosmic symphony is not yet complete. Many notes remain unresolved, many harmonies unexplored. But in the grand concert hall of science, string theory plays the role of a bold overture, an opening movement that promises a new understanding of reality's hidden structure. As Michio Kaku often says, if Einstein gave us the melody of relativity, then string theory may someday provide the full symphony. And in that music, we may finally hear the voice of the cosmos. Chapter 3. The Music of Strings, a Universe of Vibrations. The theory of strings, often referred to as string theory, begins with an audacious idea. At the most fundamental level, reality is not built from point-like particles, but from tiny filaments of energy. These filaments are unimaginably small, far smaller than atoms, even smaller than the quarks that form protons and neutrons. They are strings, and their different modes of vibration determine everything we perceive as matter and force. Imagine a violin string. Depending on how it vibrates, it produces different musical notes. In the same way, the strings of the universe vibrate in countless possible ways, and each vibration corresponds to a distinct particle. One pattern might manifest as an electron, another as a photon, another as a quark. If you zoom in far enough, beneath the particles of the Standard Model, beneath the quantum fields, what you would find, according to this theory, is a cosmic orchestra with strings humming in a symphony of existence. Michio Kaku often emphasizes that this musical metaphor is not simply poetic, it is structural. Physics is not just about equations written in chalk on blackboards. It is the search for the score of the universe, the hidden harmony that makes sense of why the cosmos is ordered the way it is. And within string theory lies the bold promise of unification. Gravity, electromagnetism, the strong force and the weak force, all different manifestations of vibrating strings. For centuries, physics has been marked by separation. Newton revealed the laws of gravity, Maxwell described electromagnetism, and later physicists uncovered the quantum nature of the strong and weak nuclear forces. But gravity resisted being merged into the quantum world. Einstein gave us general relativity, a majestic description of space and time, but it stubbornly clashed with quantum mechanics. String theory emerged as a bridge, suggesting that if we treat particles as extended strings instead of points, then gravity arises naturally, woven into the fabric of the equations. This discovery is revolutionary because it turns the chaos of forces into something deeply harmonious. In fact, the graviton, the hypothetical particle that mediates gravity, emerges inevitably from the mathematics of string theory. Unlike previous attempts to merge gravity with quantum mechanics, string theory doesn't force gravity in by hand. It is there from the beginning, one of the inevitable notes played by the cosmic strings. But harmony requires more than just sound. It requires space for vibration. And here, string theory makes one of its most radical demands: additional dimensions. The strings cannot vibrate consistently in just 3 spatial dimensions and 1 of time. They need more. According to the equations, the full music of strings requires 10 dimensions, or, in some versions, 11. Our familiar universe of length, width, and height is merely the visible tip of a far richer geometry. What happens to these hidden dimensions? Some theories suggest that they are curled up, compactified into shapes so small that we cannot perceive them. Imagine looking at a garden hose from a distance. It seems one-dimensional, just a line. But up close, you notice it has a circular dimension wrapped around it. Similarly, the extra dimensions of string theory may be wrapped so tightly that only at the scale of strings, far beyond the reach of today's microscopes or colliders, could they be explored. The geometry of these compactified dimensions is not trivial. They may form incredibly intricate shapes known as Calabi-Yau manifolds, mathematical structures that twist and fold in ways impossible to visualize fully. The way strings vibrate depends on this hidden geometry. Change the shape of the manifold and the properties of particles, mass, charge, spin, as well. In this way, the structure of our universe may be dictated by the hidden architecture of dimensions we cannot see. Michio Kaku describes this vision as a kind of cosmic design, not in a religious sense, but in the sense that the laws of physics themselves are woven from the harmonies of strings and the shapes of invisible spaces. The mind of God, as he puts it, could be thought of as cosmic music resonating through 11-dimensional hyperspace. It is not the intervention of a deity, but the profound and timeless mathematics of existence. This raises both wonder and unease. If the universe is just one possible melody, then could there be others? Could different compactifications, different shapes of hidden dimensions, give rise to entirely different physical realities, universes with laws unlike ours? String theory suggests yes. Each unique configuration of hidden geometry produces a different score for the cosmic symphony, leading to a multiverse of possibilities. Some universes might lack stable atoms, some might have no stars, others might harbor strange and exotic forms of matter. For now, we cannot step into those other realities, but the mathematics hints that they exist. Our universe, with its galaxies and stars and living beings, may be just one note in an infinite composition. This is both humbling and exhilarating. If the theory is right, then existence itself is richer than we ever dared to imagine. Of course, string theory is not without its critics. Its predictions lie far beyond the energy scales of current experiments. Particle accelerators like the Large Hadron Collider probe deep into matter, but not deep enough to reveal strings. To many scientists, this lack of testable evidence is troubling. Physics thrives on experiments, on observations that confirm or deny theories. String theory, so far, remains a majestic mathematical construct, tantalizing but unverified. Still, Michio Kaku argues that it may be the only framework vast enough to hold all the laws of physics together. Without it, unification seems impossible. With it, the universe becomes a grand symphony of vibrations, where matter, energy, space, and time are simply notes in a cosmic song. And so, the music of strings remains one of the most enchanting and controversial ideas in modern science. It invites us to see the universe not as a cold mechanism, but as a living composition, playing endlessly across the unseen dimensions of reality. Perhaps one day we will find a way to hear the full melody, and in that moment glimpse the deepest truth about why there is something instead of nothing. Chapter 4. The Hidden Dimensions. Michio Kaku often explains that the reality we perceive is just a shadow of a much deeper structure. Our senses, shaped by evolution, limit us to 3 dimensions of space and 1 of time. But the mathematics of string theory insists this is not enough. To describe the universe in its entirety, more dimensions are required, hidden, curled up so tightly that they escape detection. The idea of extra dimensions dates back to the 1920s, when Theodore Kaluza and Oscar Klein proposed that adding a 5th dimension could elegantly unify gravity and electromagnetism. Their theory was revolutionary, but quickly overshadowed by other developments in physics. Yet decades later, string theory revived this forgotten vision, declaring that the very fabric of existence cannot function without additional dimensions. Depending on the version, the theory requires 10 or 11 dimensions, a universe far richer than our ordinary perception suggests. Kaku describes these dimensions as invisible directions, compactified into unimaginably tiny scales, perhaps as small as the Planck length. If one could shrink down to that scale, these hidden realms might unfold like an intricate origami, revealing landscapes of infinite complexity. Some physicists imagine them as tiny loops or spheres, others as exotic shapes known as Calabi-Yau manifolds. Why are these dimensions necessary? In the framework of string theory, they provide the resonant chambers in which strings vibrate. Just as the body of a violin shapes its sound, the geometry of these extra dimensions determines the notes of vibrating strings, which in turn correspond to the particles and forces we observe. Electrons, quarks, photons, all may be nothing more than echoes of strings resonating within hidden dimensions. For Kaku, this revelation is more than abstract mathematics. It is the key to understanding why the universe is the way it is. If the hidden dimensions were shaped differently, the fundamental constants of nature could change. Atoms might not form. Stars might not ignite. Life as we know it would be impossible. In this view, our universe is not arbitrary. It is a consequence of the geometry of unseen dimensions sculpting the laws of physics. Kaku often paints vivid analogies to make these ideas approachable. He invites us to imagine ants crawling along a garden hose. To the ants, the hose looks like a 2-dimensional surface. They can move forward and backward. But if we zoom out, we see the hose is actually 3-dimensional, with a circular dimension curled up too tightly for the ants to notice. Similarly, our universe may contain hidden dimensions invisible to us, yet real and essential to its structure. This concept also opens the door to the possibility of parallel worlds. If the extra dimensions are not tightly curled, but extended, there could be entire universes floating parallel to ours, separated by imperceptible distances. In string theory, these are called branes, multi-dimensional surfaces where whole universes can reside. Our universe may be one brane among countless others, drifting in a higher dimensional ocean. The implications are staggering. If true, then the cosmos is far larger than we ever dared to imagine. The stars above are no longer the only beacons of existence. Beyond our horizon, hidden by the veil of dimensions, other universes could shine with their own galaxies, their own laws, perhaps even their own versions of life. For Kaku, exploring hidden dimensions is not only about science, but about expanding the human imagination. It challenges us to step beyond the narrow limits of our perception and to glimpse a reality that transcends the boundaries of space and time. To him, physics is not just a tool for equations, but a gateway to the cosmic cathedral where hidden dimensions are the pillars of existence. And in that vision, the great mystery is not whether these dimensions exist, but whether one day we will find a way to enter them, to journey beyond the shadows of our familiar world and into the deeper architecture of the multiverse. Chapter 5. The Unification of Cosmic Forces. One of the most enduring quests in physics has been the search for unification. From Newton to Einstein, scientists have sought a single framework that can explain the forces that govern the universe. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These four fundamental interactions dictate the behavior of matter and energy, yet they have historically appeared as separate, disconnected phenomena. Michio Kaku often reflects on Einstein's dream of a unified field theory. Einstein believed that the diversity of forces could be reduced to a single principle, a law so elegant that it would describe all of reality. While Einstein made tremendous strides with general relativity, which elegantly described gravity and the curvature of space-time, he could not reconcile it with quantum mechanics, which governs the subatomic realm. String theory offers a path forward. In Michio Kaku's vision, the universe is not composed of isolated particles, but of vibrating strings, and the way these strings resonate determines the type of force they carry. Gravity emerges naturally as one of the vibrational modes, while other modes manifest as the electromagnetic, strong, and weak nuclear forces. In this way, string theory promises a unification that has eluded physicists for a century. To understand this, imagine the universe as a grand musical instrument, with strings vibrating to produce different sounds. One vibration produces gravity, another generates electromagnetic waves, another produces the strong nuclear force, holding atomic nuclei together. Each note is unique, yet all arise from the same underlying string. The diversity of forces is thus unified by the harmony of vibrations. The theory also suggests that the properties of these forces depend on the hidden dimensions of the universe. The shape and size of compactified dimensions dictate the strengths and characteristics of each interaction. Alter the geometry, and the laws of physics themselves would change. Kaku emphasizes that this is not mere speculation. It is a consequence of the mathematical structure of string theory. The unification of forces is more than a theoretical ambition. It offers the promise of understanding why the universe exists in the form it does. Why do electrons have the mass they do? Why is gravity so much weaker than electromagnetism? Why do protons and neutrons form stable atoms? In Kaku's framework, these are not arbitrary questions, but reflections of the hidden geometry of higher dimensions and the vibrational patterns of strings. Kaku often notes that this unification has practical implications, even if subtle. The search for a theory of everything is not just a philosophical exercise. It shapes the questions we ask in particle physics, cosmology, and quantum mechanics. Experiments at particle colliders, observations of cosmic microwave background radiation, and studies of black holes all test the boundaries of these unified principles, even if indirectly. Yet challenges remain. String theory, in its current form, offers a vast landscape of possible solutions, perhaps 10 to the 500 different ways to compactify extra dimensions. Each solution corresponds to a different universe with different laws. While this is exciting, it also makes predictions difficult. How can we determine which configuration corresponds to our universe? Kaku suggests that subtle cosmic fingerprints, patterns in the cosmic microwave background, the distribution of galaxies, or gravitational wave signals might one day provide clues. Beyond the technical details, the beauty of unification lies in its elegance. Kaku emphasizes that physics is not just a catalog of phenomena, but a pursuit of simplicity and coherence. The discovery that all forces may arise from a single underlying principle is a testament to the deep order of the cosmos. Ultimately, the unification of cosmic forces embodies the human desire to see the universe as comprehensible and interconnected. In string theory, in the vibrations of hidden strings and the folds of extra dimensions, Kaku glimpses a cosmos where gravity, electromagnetism, and the nuclear forces are not separate, conflicting entities, but notes in a single, magnificent symphony, a harmony waiting for us to hear it. Chapter 6: Quantum Loops and the Fabric of Reality. As we explore the deeper layers of string theory, one concept becomes increasingly central: the idea that the universe is not a static stage, but a dynamic, vibrating fabric. Michio Kaku often describes reality as a complex tapestry, where space-time itself is interwoven with energy, particles, and the fundamental vibrations of strings. The quantum world is alive with fluctuations, loops, and oscillations, all of which contribute to the phenomena we observe at larger scales. In classical physics, space and time were seen as smooth and continuous, a stage on which events unfolded. Einstein revolutionized this perspective by revealing that space-time could bend, warp, and stretch under the influence of mass and energy. Yet even general relativity cannot fully account for the quantum microcosm, where particles appear and vanish, probabilities dominate, and uncertainty reigns supreme. String theory, Kaku suggests, offers a bridge between these worlds. The concept of quantum loops emerges naturally in this framework. These loops are tiny, self-contained circuits of energy and information, microscopic structures that twist and fold within space-time. They represent potentialities, vibrating patterns that define the properties of particles and forces. In essence, loops are the scaffolding upon which the symphony of strings performs, providing a dynamic backdrop to the melody of existence. One of the most striking features of quantum loops is their role in unifying gravity with quantum mechanics. Traditionally, attempts to quantize gravity, treat it with the same probabilistic laws as other forces, resulted in infinities and inconsistencies. But in string theory, these loops allow gravity to be incorporated naturally, smoothing out the singularities that plague traditional quantum gravity. Kaku often likens this to weaving a complex fabric. The loops are the threads that prevent the tapestry from tearing under the strain of extreme forces. Another profound implication involves the multiverse. Each vibrational pattern, each loop configuration may correspond to a distinct universe. If strings can oscillate in myriad ways, and if loops can fold into countless topologies, then the cosmos may contain an infinite number of universes, each with its own physical laws. Some universes might mirror our own closely. Others could be entirely alien, with dimensions, particles, or forces unfamiliar to us. Kaku emphasizes that this is not merely abstract speculation. Mathematics dictate these possibilities, and the patterns of string vibrations and quantum loops are bound by strict rules. The universe, in this sense, is both creative and constrained, a dynamic interplay between freedom and necessity. The laws of physics we observe are the emergent properties of these deeper structures, much like the shape of a musical chord emerges from the vibrations of individual strings. The interplay of loops also offers a new lens through which to view cosmic evolution. Black holes, the extreme warps of space-time, may be understood as regions where loops condense, collapse, and interact in complex ways. The early universe, moments after the Big Bang, may have been dominated by a froth of loops and vibrating strings, setting the stage for the formation of matter, stars, and galaxies. Michio Kaku often reflects on the philosophical implications of this vision. If the universe is woven from loops and strings, then reality is not a collection of isolated objects, but a dynamic network of relationships. Space, time, matter, and energy are intertwined, and our very existence is part of this unfolding cosmic dance. Understanding these loops, even abstractly, allows us to glimpse the underlying order of the cosmos and our place within it. Ultimately, quantum loops remind us that reality is both stranger and more beautiful than we imagine. It is not static, not fully knowable, but alive with vibrations and possibilities. In Kaku's vision, every particle, every wave, every flicker of energy is part of a vast and intricate orchestra, a living testament to the elegance of the universe, echoing through dimensions we are only beginning to perceive. Chapter 7. Parallel Realities. The Multiverse Unveiled. One of the most compelling ideas in Michio Kaku's exploration of the cosmos is the concept of the multiverse. Beyond the universe we perceive lies a vast expanse of parallel realities, each with its own unique physical laws, histories, and potentialities. This notion is not pure fantasy, but a natural consequence of string theory, quantum mechanics, and cosmological principles, suggesting that the cosmos is far more intricate and diverse than we could ever imagine. Kaku often frames the multiverse as a spectrum of possibilities. At one end lies the universe we inhabit, with galaxies, stars, and life as we know it. At the other, there exist realms so different that the familiar rules of matter, energy, and time may no longer apply. Some universes may be nearly identical to our own, differing only in minor ways, a flipped coin here, a divergent evolution of species there. Others may be entirely alien, where chemistry, light, or gravity behave in unimaginable ways. This idea is reinforced by the mathematics of string theory. Each possible vibration of a string, combined with the configuration of hidden dimensions, generates a distinct universe. With potentially 10 to the 500 different ways to fold these dimensions, the multiverse becomes almost unimaginably vast. Our universe may be a single note in an infinite cosmic symphony, one melody among countless others. The multiverse also finds support in cosmology. The inflationary model, which describes the rapid expansion of space moments after the Big Bang, suggests that pockets of space could stop inflating at different times, giving birth to bubble universes. Each bubble might evolve independently, producing different laws of physics. In Kaku's interpretation, these cosmic bubbles are not mere speculation. They are a natural outcome of the fundamental dynamics of space, energy, and strings. Kaku often invites his audience to consider the philosophical implications of parallel realities. If there are countless universes, each governed by its own principles, what does that say about the uniqueness of our existence? Are we exceptional, or one version of many possibilities? And if our universe is just a single thread in an infinite tapestry, how does that reshape our understanding of meaning, destiny, and choice? Quantum mechanics adds yet another layer of complexity. The famous many worlds interpretation suggests that every quantum event, every decision, every collision of particles branches into multiple outcomes, creating parallel realities at every moment. From this perspective, the multiverse is not only spatial, but temporal, a continuously branching tree of possibilities where every alternative is realized somewhere. Kaku emphasizes that while these ideas may seem abstract, they are grounded in rigorous mathematics and theoretical physics. Detecting other universes directly remains beyond our current capabilities, but subtle clues may exist in cosmic radiation, gravitational waves, or anomalies in the cosmic microwave background. Every experiment brings us a step closer to understanding whether the multiverse is a mathematical curiosity or a tangible extension of reality. Beyond science, the concept of parallel realities inspires wonder. It challenges our sense of scale, our notions of fate, and even our understanding of life itself. In Kaku's vision, consciousness may not be confined to a single universe. The mind could, in principle, resonate with the multiverse, perceiving the echoes of existence beyond our own bubble of reality. The multiverse also offers hope and perspective. If our universe is fragile, one among many, then the vast cosmos is resilient. New universes may emerge, alternate realities may flourish, and the grand symphony of existence continues, irrespective of the fate of any single world. In the end, Michio Kaku presents the multiverse not as a remote abstraction, but as a profound invitation to expand our imagination, to question the limits of perception, and to recognize that reality is more intricate, more mysterious, and more beautiful than we have ever dared to imagine. Chapter 8. Implications for Cosmology and Life. As we peer deeper into the universe through the lens of string theory and the multiverse, the questions naturally expand beyond particles and forces. They touch the origins of galaxies, stars, and even life itself. Michio Kaku emphasizes that the patterns of strings and the shape of extra dimensions are not abstract curiosities. They set the stage for everything we observe in the cosmos. The early universe, immediately following the Big Bang, was a seething, turbulent sea of energy. Strings vibrated, loops twisted, and hidden dimensions shaped the conditions under which matter could coalesce. The properties of fundamental particles, dictated by these vibrations, determined the formation of atoms, the chemistry of stars, and ultimately the emergence of complex elements like carbon and oxygen, the building blocks of life. Kaku often illustrates this with analogies. Imagine baking a cake. the final flavor depends not just on the ingredients, but on the precise temperature and timing. Similarly, the universe's physical constants are finely tuned, a consequence of string vibrations and the geometry of hidden dimensions. Alter one subtle parameter, and stars might never ignite, atoms might not form, and life would be impossible. In this sense, string theory provides a framework to understand why the universe is just right for life. This framework also invites speculation about life in other universes. If the multiverse exists, then some universes may have similar conditions to ours, where chemistry and biology can unfold. Others may be starkly different, with laws of physics so alien that life as we know it could never arise. Kaku encourages us to imagine these possibilities, not as science fiction, but as logical consequences of mathematical structures underlying reality. Furthermore, string theory reshapes cosmological thinking. Black holes, cosmic inflation, and the distribution of galaxies are all influenced by the vibrations of strings and the properties of extra dimensions. Tiny quantum fluctuations in the early universe, amplified by inflation, became the seeds for galaxy formation. In this sense, the cosmic landscape we see today, the Milky Way, distant quasars, cosmic filaments, is a grand manifestation of the microscopic dance of strings billions of years ago. Kaku also reflects on consciousness and life in this context. If the universe is structured by vibrational patterns, then the emergence of life is a natural outcome of these patterns interacting over cosmic time. Life is not random chaos, but an emergent phenomenon arising from the elegant mathematical structure of the cosmos. Humans, with our curiosity and imagination, are participants in this cosmic unfolding, capable of perceiving and contemplating the underlying order of reality. Ultimately, the implications are profound. The study of strings, hidden dimensions, and multiverses is not merely an intellectual exercise. It is a bridge connecting the microscopic to the cosmic, the theoretical to the observable, and science to the human quest for meaning. In Kaku's vision, understanding the universe is inseparable from understanding our place within it. Chapter 9. Experiments and the Future of Testing String Theory. String theory, for all its elegance, faces a formidable challenge. It is notoriously difficult to test directly. The strings themselves are far too small to observe with current technology, and the extra dimensions they require are hidden from everyday perception. Yet Michio Kaku emphasizes that this does not make the theory unscientific. Through indirect observation, mathematical consistency, and creative experimentation, physicists are devising ways to explore the hidden layers of reality. One of the most promising approaches involves high-energy particle physics. Colliders like the Large Hadron Collider, LHC, at CERN, push matter to extreme energies, mimicking conditions similar to those moments after the Big Bang. By studying the behavior of fundamental particles under these extreme conditions, scientists can test predictions that align with string theory. For example, certain supersymmetric particles or subtle anomalies in particle interactions could provide evidence of extra dimensions or string effects. Cosmology also offers clues. The cosmic microwave background, the faint afterglow of the Big Bang, carries imprints of the universe's earliest moments. Tiny fluctuations in this radiation may reveal signatures of strings or hidden dimensions, patterns that could help distinguish string theory from competing models. Gravitational waves, ripples in space-time detected by instruments like LIGO, may also hold hints of primordial string vibrations, providing a new window into the fabric of reality. Kaku often highlights that the testing of string theory is as much about innovation as observation. Future technologies, from ultra-powerful colliders to space-based observatories, may one day probe energy scales where string effects become detectable. Meanwhile, theoretical work continues to refine predictions, narrowing the vast landscape of possible string configurations. Each constraint, each mathematical insight brings us closer to bridging the gap between theory and experiment. Another avenue of exploration lies in the multiverse. While direct observation of other universes is currently impossible, their influence may leave subtle fingerprints in our own cosmos. Patterns in galaxy distribution, anomalies in cosmic radiation, or unexpected gravitational effects could hint at interactions with neighboring universes or the consequences of higher dimensional spaces. Kaku envisions a future where careful observation and theoretical modeling converge to provide indirect yet compelling evidence of the multiverse. The implications of these experiments extend beyond physics. They reshape our understanding of reality itself, testing ideas that once belonged solely to philosophy or science fiction. In Kaku's vision, experimentation becomes a dialogue with the cosmos. Each measurement, each anomaly, is a note in the symphony of discovery, gradually revealing the deeper structures that govern existence. Finally, Kaku emphasizes the human element. The pursuit of string theory and the multiverse is not just about equations or particles. It is a testament to curiosity, imagination, and perseverance. Each experiment, whether confirming a subtle prediction or disapproving a hopeful hypothesis, deepens our knowledge and expands the boundaries of possibility. The future of testing string theory is not merely a scientific challenge, it is a journey toward understanding the very essence of the cosmos. Chapter 10: Philosophy and the Cosmic Mind. As we arrive at the culmination of Michio Kaku's vision, it becomes clear that string theory and the multiverse are not merely scientific frameworks. They are lenses through which we can explore the deepest questions of existence. Kaku often reflects on the philosophical and humanistic implications of his work. If the universe is woven from strings and composed of countless parallel realities, what does that mean for consciousness, destiny, and our search for meaning? In this cosmic perspective, reality is both ordered and dynamic. Every vibration, every hidden dimension, every potential universe contributes to the grand tapestry of existence. Human consciousness emerges not in isolation, but as part of this intricate network, a phenomenon shaped by the fundamental patterns of reality itself. Kaku suggests that understanding the universe is inseparable from understanding ourselves. As we explore the cosmos, we also illuminate the nature of mind and awareness. The multiverse challenges traditional notions of uniqueness and fate. If infinite realities exist, each representing alternative possibilities, then every choice we make, every action, may resonate across dimensions. This perspective fosters both humility and wonder. We are participants in a vast cosmic experiment, capable of influencing the unfolding of events within our universe, yet aware of the larger mysterious structure in which all realities coexist. Kaku also emphasizes the unity underlying apparent diversity. Gravity, electromagnetism, the strong and weak nuclear forces all emerge from the same vibrational fabric of strings. Similarly, the multiverse, with its infinite possibilities, emerges from the same fundamental principles. This harmony reveals a profound coherence in nature, suggesting that the cosmos is not random chaos, but a well-orchestrated symphony waiting to be understood. Beyond science, Kaku invites us to consider the ethical and spiritual dimensions. If we are aware of the vast possibilities inherent in the cosmos, then our responsibility to ourselves, each other, and the universe becomes clearer. Knowledge of the multiverse and string theory is not merely intellectual, it is a call to curiosity, compassion, and stewardship of the world we inhabit. Finally, the cosmic mind, the idea that the universe has an underlying intelligence or order, offers a sense of awe that transcends scientific inquiry. Kaku reminds us that the pursuit of a theory of everything is ultimately a pursuit of understanding. The deep, elegant structure that allows stars to shine, planets to form, life to emerge, and consciousness to ponder its own origins. In exploring these mysteries, we connect with something greater than ourselves, a universe both comprehensible and infinitely mysterious. In this final reflection, string theory and the multiverse serve as bridges between physics, philosophy, and imagination. They remind us that science is not only about measurement, but about vision. By peering into hidden dimensions, listening to the vibrations of strings, and contemplating the multiplicity of worlds, we come closer to answering the eternal question: what is our place in the cosmos? Michio Kaku's work invites us to explore, to wonder, and to dream, revealing a universe that is far richer, stranger, and more beautiful than we ever imagined. Conclusion: reflecting on the infinite. As we conclude our journey through strings, loops, hidden dimensions, and parallel universes, a profound sense of wonder emerges. Michio Kaku's vision reminds us that the universe is far more intricate than our daily perceptions allow. A vast tapestry woven from vibrations, possibilities, and mathematical elegance. Every chapter of this exploration, from the fabric of reality to the branching multiverse, from quantum loops to cosmic symphonies, reveals layers of complexity and beauty that challenge our imagination and expand our understanding. Yet beyond the equations and theories lies a human story, a story of curiosity, persistence, and the relentless desire to understand. Kaku's work exemplifies how the pursuit of knowledge connects us to something larger than ourselves. Each discovery, each theoretical insight invites reflection on our place in the cosmos and the nature of existence itself. The implications are both scientific and philosophical. We have seen how string theory unifies forces, how quantum fluctuations shaped galaxies, and how parallel realities suggest infinite possibilities. But we have also glimpsed a deeper message, that reality is interconnected, dynamic, and alive with potential. The cosmos is not a static backdrop. It is a living, resonant system, and humanity is part of its ongoing evolution. In the end, the journey through the multiverse and the vibrations of strings is also a journey inward. It challenges us to think expansively, to embrace uncertainty, and to cultivate awe. The mysteries of the universe, its hidden dimensions, its infinite possibilities, its cosmic symphony, invite us to expand our perspective, deepen our imagination, and consider the profound beauty of existence. As we close this exploration, Let us carry forward the curiosity and wonder that Michio Kaku inspires. Let us gaze at the stars not only with our eyes, but with our minds, attuned to the hidden harmonies that underpin reality. The universe, in all its mystery and magnificence, continues to unfold, and in that unfolding, we find both knowledge and inspiration, reminding us that the universe is a boundless canvas for imagination, discovery, and human understanding.